Imagine standing at the edge of everything that exists, not at the edge of a country or a continent or even a planet, but at the absolute boundary of reality itself, where space curves into mystery and time dissolves into questions we're only beginning to understand how to ask. Behind you stretches everything that light has had time to reach since the beginning. Before you lies, what? More universe? Different laws of physics? Or simply nothing? An unknowable beyond that exists but remains forever hidden from view. This is the observable universe, and we now know, with astonishing precision, exactly how vast it truly is. For millennia, humans believed the cosmos was small, intimate, centered on Earth. The stars were thought to be painted on a celestial sphere just beyond the wandering planets. Then telescopes arrived, and the sphere shattered. We discovered that stars were distant suns, that our sun was merely one among billions, that our galaxy was only one island in an ocean of galaxies stretching farther than anyone had dared to imagine. But even as our understanding expanded, a fundamental question remained. How big is it all? Not just the part we can see with our current instruments, but the part we could ever see, even in principle. Where does observable reality end? And what does it even mean for the universe to have an edge? Tonight, we journey to that edge. We will trace a path from the familiar ground beneath our feet to the most distant light in existence, following a cosmic timeline measured not in years or centuries, but in billions of years, across distances so vast that numbers themselves begin to lose meaning. This is not simply a story of size, it is a story of light, time, expansion, and the strange geometry of a universe that is somehow both finite in what we can observe and possibly infinite in what exists beyond our cosmic horizon. Recent measurements, powered by revolutionary instruments like the James Webb Space Telescope, the Planck satellite, and decades of careful observation, have given us the most accurate picture yet of our cosmic neighbourhood's true scale. The observable universe, the bubble of space from which light has had time to reach us since the Big Bang, stretches approximately 93 billion light-years in diameter, not 13.8 billion, as you might expect from the universe's age, but 93 billion. This discrepancy itself is a profound mystery, one we will gently unravel as we drift through the cosmic dark together. How can the universe be older than 13.8 billion years, yet the edge lie 46.5 billion light-years away in every direction? The answer lies in something both elegant and unsettling. The universe itself is expanding, and has been since the moment of its birth. Space is not static. It grows, stretches, carries galaxies with it, like leaves on an ever-widening river. Light that began its journey toward us billions of years ago has been travelling through space that was simultaneously stretching beneath it, extending the distance even as the light raced to close it. We stand at the centre of our own observable sphere, not because we are special, but because observation itself creates the boundary. Every point in the universe is the centre of its own observable bubble. An alien astronomer in a galaxy 10 billion light-years away would see a different cosmic horizon, a different edge, overlapping with ours, but never quite the same. We are all, everywhere, standing at the centre of our own visible infinity. Tonight's journey will take us from the scale of human hands to the scale of galactic superclusters, from the familiar dance of planets to the cosmic web of dark matter that scaffolds all visible structure. We will visit the ancient light of the cosmic microwave background, the afterglow of creation itself still cooling after nearly 14 billion years. We will contemplate what it means that we can see the past, that every photon entering our telescopes is a messenger from a younger universe, and that the farther we look, the further back in time we travel. This is a journey best taken slowly, with patience and wonder. Whether you're drifting towards sleep, studying the cosmos, or simply seeking a moment of contemplation beneath the weight of ordinary life, you are welcome here. Let the scale wash over you. Let the numbers become poetry. There is no test at the end, only awe. If you are joining us on this voyage through space and time, we would love to know, where are you watching from tonight? What time is it in your corner of the world? Leave a comment below. It is a small reminder that while we explore the larger structures in existence, we remain connected, human, sharing this singular moment across the surface of our small blue world. Now, settle in. Dim the lights if you can. And let us begin our ascent toward the edge of everything together. Before we can comprehend the vastness of the observable universe, we must first understand what the word observable truly means. It is not a measure of human ability or technological advancement. It is a fundamental boundary written into the fabric of reality itself, shaped by the speed of light and the finite age of time. The observable universe is not everything that exists. It is everything we can possibly see, measure, or detect from our vantage point in space and time. It is the portion of the cosmos from which light has had enough time to reach us since the beginning, since the moment 13.8 billion years ago, when the universe began its expansion in an event we call the Big Bang. Light travels fast, unimaginably fast. At 186,000 miles per second, it crosses the distance from the Moon to Earth in just over 1 second. Yet even at this tremendous speed, light is still bound by time. The universe has only existed for 13.8 billion years, and so light from regions farther than a certain distance simply hasn't had time to reach us yet. It is not that those regions don't exist. It is that we're separated from them not by space alone, but by the passage of time itself. This creates a horizon, not unlike the horizon on Earth where the sky meets the sea. But this is a cosmic horizon, an information barrier that surrounds us in every direction. Beyond this boundary, events unfold, galaxies form, stars ignite and die, but their light has not yet crossed the void to touch our instruments. They exist in a realm beyond observation, beyond confirmation, beyond reach. What lies beyond this horizon may be infinite. The entire universe, the totality of everything that exists, could extend forever in all directions, filled with countless galaxies, structures, and worlds we will never see. Or it could be finite, curved back upon itself in ways our minds struggle to visualize. We do not know, we may never know. What we do know is that the observable universe, the sphere of space from which light can reach us, is distinct and limited. Yet this limit is not static. It is not simply a sphere with a radius of 13.8 billion light-years. The universe itself has been expanding since its birth, and not just expanding, but accelerating. Space itself stretches, carrying galaxies away from one another, and this expansion complicates our understanding of cosmic distance in profound ways. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us than it is now. As the light travelled through space toward Earth, space itself expanded, stretching the distance between us and that galaxy. By the time the light reaches our telescopes today, the galaxy has moved much farther away. In fact, the most distant objects we observe today are now more than 46 billion light-years away, even though their light has been travelling for less than 13.8 billion years. This is why the observable universe has a radius not of 13.8 billion light-years, but approximately 46.5 billion light-years. The expansion of space transforms our cosmic horizon into something more complex than a simple sphere of light travel time. It becomes a dynamic boundary, one that shifts and grows as the universe ages, as light continues its journey, and as space continues to stretch. To stand at the center of the observable universe is to recognize that we're not at the center of everything. We are at the center of our own observation, our own sphere of visibility. Every point in the universe is the center of its own observable universe. An observer on a distant galaxy billions of light years away would see their own cosmic horizon, their own boundary of light and time. They would see galaxies we cannot see, while missing galaxies visible to us. Each observer occupies their own unique pocket of observability, isolated by distance and the finite speed of information. This is not a limitation of technology. It is a feature of the cosmos itself. Even if we could build instruments of infinite sensitivity, even if we could detect the faintest whisper of light across the void, we could not see beyond the observable universe. The light from those regions has not yet arrived. It may never arrive, for as space expands, some regions are moving away from us faster than light can travel through space to reach us. These regions are crossing a threshold beyond which they will fade from view forever, disappearing beyond an event horizon, not of a black hole, but of cosmic expansion itself. The farthest edge of our observable universe is not empty space or distant galaxies. It is something far more ancient and far more profound. It is the cosmic microwave background radiation, the afterglow of the Big Bang itself. This faint glow fills the sky in every direction, a relic of the moment, roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. Before this moment, the universe was opaque, filled with a hot, dense plasma that scattered light in every direction. Photons could not travel far before colliding with particles. The cosmos was a fog, impenetrable to observation. But as the universe expanded and cooled, electrons combined with nuclei to form neutral atoms, and the fog cleared. Light was released, streaming outward in all directions, and it has been travelling ever since. Today that light reaches us as microwave radiation, stretched by the expansion of space from visible light into the microwave spectrum. It appears as a nearly uniform glow across the entire sky, with tiny fluctuations that reveal the seeds of galaxies, the density variations that would eventually collapse under gravity to form stars, planets, and us. The cosmic microwave background is the oldest light we can see, a snapshot of the universe in its infancy, and it marks the edge of electromagnetic observation. Beyond this wall of light, we cannot see with telescopes. The universe before that moment is hidden, not by distance, but by opacity. It is a frontier of knowledge, a boundary that defines what we can learn through light alone. Yet observation is not limited to light. The universe speaks in other languages, and future technologies may allow us to listen in ways we have only begun to imagine. Gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, travel unimpeded through matter and radiation. They carry information from moments closer to the Big Bang than the cosmic microwave background, perhaps even from the first fractions of a second when the universe was unimaginably hot and dense. Neutrinos, ghostly particles that interact weakly with matter, also carry messages from the early universe. They pass through stars, planets, and entire galaxies as if they were not there. Detecting them is extraordinarily difficult, but they offer a window into processes hidden from electromagnetic observation. If we could build detectors sensitive enough, we might observe the universe in neutrinos peering into epochs even older than the cosmic microwave background. But even these methods have limits. There are boundaries beyond which no information can reach us, not because our instruments are inadequate, but because the universe itself prevents it. The observable universe is not just a region we can see, it is a region we can know. Beyond it lies not just the unseen, but the unknowable, at least from our current position in space and time. To understand what observable really means is to accept a humbling truth. We are surrounded by mystery. The universe we observe, vast and filled with billions of galaxies, may be only a tiny fraction of everything that exists. The rest is beyond our horizon, beyond our reach, separated from us by the very structure of reality. We live in a bubble of light and information, floating in an ocean of unknowable expanse. Yet this boundary does not diminish the significance of what we can observe. It amplifies it. Every photon that reaches us, every signal we detect, is a message from the past, a fragment of cosmic history that has travelled across billions of years to arrive at this moment. To observe the universe is to receive letters written in the language of light, sent from worlds and epochs that no longer exist in the forms we see them. The observable universe is not a prison. It is a stage. It is the arena in which we can explore, measure, and understand. It is the canvas upon which the story of cosmic evolution is painted. From the first moments after the Big Bang to the formation of galaxies, stars, and planets, to the emergence of life, consciousness, and the ability to look outward and ask, how far does it go? The answer for now is 46.5 billion light-years in every direction. But the true answer is deeper. It goes as far as light and time allow. It goes to the edge of knowability itself. And beyond that edge, the universe continues, vast and silent, waiting for the day when new technologies or new physics might reveal what lies in the darkness beyond our horizon. Understanding what observable really means is understanding that the universe is not just a place. It is a relationship between space, time, and information. It is a reminder that we are not just observers of the cosmos, but participants in it, bound by the same laws that govern stars and galaxies, light and distance. We are creatures of time, living in a universe where the past is visible, the future is uncertain, and the present is the only moment from which we can truly see. 93 billion light-years. The number itself feels almost meaningless at first, like trying to count grains of sand by imagining oceans. And yet, this is the stage upon which everything we can ever observe unfolds. This is the diameter of the observable universe, the outermost boundary of light that could have reached us since the beginning of time. But how did we arrive at this number? And more profoundly, what does it truly mean? The journey to understanding this measurement is not one of simple arithmetic. It is a story woven from starlight and mathematics, from ancient photons and quantum uncertainty, from telescopes that peer into the past and equations that describe the fabric of space-time itself. To comprehend 93 billion light-years is to grasp something fundamental about the nature of reality, that the universe is older than the distance light has travelled, that space itself can expand faster than light, and that what we see is not what is, but what was. Our universe is 13.8 billion years old. At first glance, one might assume the observable universe should therefore extend 13.8 billion light-years in every direction, a sphere with a radius equal to the age of the cosmos multiplied by the speed of light. Simple, intuitive, and profoundly incorrect. The actual radius of the observable universe is not 13.8 billion light-years, it is 46.5 billion light-years. The diameter therefore stretches to 93 billion light-years, edge to edge. This discrepancy is not an error in measurement, it is a revelation about the very nature of space. The key lies in understanding that space itself is not static. The universe does not merely contain objects moving through space. The space between those objects is expanding, stretching, like the surface of a balloon being inflated. This is metric expansion, and it obeys rules far stranger than the motion of particles. When we look at distant galaxies, we are not simply seeing objects that have travelled away from us. We are seeing objects whose light has been journeying toward us, while the space between us and them has been growing all along. Imagine a photon of light, born in the fiery aftermath of the Big Bang, racing toward the place where Earth will one day form. As it travels, space itself stretches beneath it. The photon covers distance, yes, but that distance is simultaneously being elongated by expansion. By the time the photon finally reaches us billions of years later, the object that emitted it is no longer where it appeared to be. It has been carried farther away by the expansion of space. Much farther. The light we receive today might have travelled for 13 billion years, but the galaxy that emitted it is now more than 40 billion light-years away. This is the distinction between co-moving distance and proper distance. Co-moving distance accounts for the expansion of space, measuring where an object is now at this very moment, even though we cannot see it in its current location. Proper distance, by contrast, measures where the object was when the light we see left it. These two distances diverge dramatically at cosmic scales, and understanding this divergence is essential to grasping why the observable universe is so much larger than its age suggests. The foundation of this measurement rests on decades of painstaking observation. In the 1920s, Edwin Hubble discovered that galaxies are receding from us, and that the farther away they are, the faster they move. This relationship, now known as Hubble's law, revealed that the universe is expanding. The rate of this expansion is quantified by the Hubble constant, a number that describes how quickly space grows over cosmic distances. For decades, astronomers worked to refine this constant, using increasingly sophisticated methods to measure the velocities and distances of galaxies. One of the most powerful tools in this endeavour came from type I supernovae. These stellar explosions occur when white dwarf stars reach a critical mass and detonate with remarkably consistent brightness. Because their intrinsic luminosity is known, astronomers can measure how far away they are by comparing their apparent brightness to their true brightness. By observing supernovae in distant galaxies and measuring how fast those galaxies are receding, scientists calculated the expansion rate with unprecedented precision. These observations revealed not only that the universe is expanding, but that the expansion is accelerating, driven by a mysterious force we now call dark energy. Another cornerstone of our understanding comes from the cosmic microwave background, the faint afterglow of the Big Bang itself. This radiation, emitted when the universe was only 380,000 years old, has travelled across the entire expanse of observable space to reach us today. Satellites like COBE, WMAP, and Planck have mapped this ancient light with extraordinary detail, revealing minute fluctuations in temperature that correspond to the density variations in the early universe. From these fluctuations, cosmologists extract information about the universe's composition, its geometry, and its rate of expansion. The cosmic microwave background is not merely a relic, it is a blueprint, encoded with the parameters that govern the cosmos. By combining data from supernova, the cosmic microwave background, and observations of distant galaxies, scientists have refined the Hubble constant to within a few percentage points. Current estimates place it at approximately 70 km per second per megaparsec. This means that for every 3.26 million light-years of distance, space expands at a rate of 70 km per second. At cosmic scales, this adds up rapidly. Galaxies billions of light-years away are receding from us at velocities that exceed the speed of light, not because they are moving through space faster than light, but because the space between us and them is expanding faster than light can traverse it. This does not violate Einstein's theory of relativity. Relativity constrains the motion of objects through space, not the expansion of space itself. The mathematics that connect the universe's age to its size are elegant but complex. When cosmologists calculate the observable universe's radius, they integrate the expansion history of space from the Big Bang to the present. They account for how the expansion rate has changed over time, influenced by the density of matter, radiation, and dark energy. In the early universe, when matter and radiation were densely packed, expansion was rapid but decelerating. As the universe grew and matter spread out, dark energy began to dominate, causing the expansion to accelerate once more. These shifting dynamics mean that space has expanded non-uniformly over cosmic history. The result of this calculation, when all factors are included, yields a radius of approximately 46.5 billion light-years. A sphere of observation centered on Earth, stretching outward to the most distant light that could have reached us, encompassing a diameter of 93 billion light-years. Yet even as our measurements have grown more precise, they have also revealed tensions. Different methods of measuring the Hubble constant do not always agree. Observations of the cosmic microwave background yield a slightly different value than measurements based on supernova and nearby galaxies. This discrepancy, known as the Hubble tension, is subtle but persistent. It suggests that our understanding of the universe may be incomplete, that some factor we have not yet accounted for may be influencing the expansion rate. Perhaps dark energy behaves differently than we assume. Perhaps there are particles or forces yet to be discovered. The Hubble tension is not merely a problem. It is a doorway, an invitation to explore deeper mysteries. The precision with which we now know the size of the observable universe is staggering. A century ago, astronomers debated whether galaxies existed beyond the Milky Way. 50 years ago, the age of the universe was uncertain by billions of years. Today, we know the universe's age to within 20 million years, a precision of better than 0.15%. We know its size to within a few hundred million light-years, a margin of error that would have seemed inconceivable to earlier generations. This achievement is not the work of a single discovery, but the cumulative effort of thousands of scientists, decades of observation, and instruments that push the boundaries of technology and human ingenuity. To stand before the number 93 billion light-years is to stand before the product of light and time, distance and expansion. It is a number that encompasses every star we will ever see, every galaxy that could ever be observed, every photon that has journeyed across the cosmos to reach our eyes. It is the finite boundary of an infinite question. Beyond this edge lies space that is expanding away from us so rapidly that its light will never reach us. There may be galaxies there, perhaps infinite in number, but they exist beyond the horizon of observation, forever hidden by the limits of light and time. The observable universe is not the universe. It is our universe, the portion of existence that we can touch with light and mathematics. It is shaped not only by the physics of expansion, but by our position in time. An observer in a distant galaxy, billions of light-years away, would see a different observable universe centered on their location, overlapping with ours in some regions but extending into realms we can never see. The observable universe is not a place, it is a perspective, and yet within this perspective lies everything we have ever known. Every atom in our bodies was forged in stars that existed within this sphere. Every photon that illuminates our world travelled through this expanse. The 93 billion light-years that stretch around us are not merely a measurement of distance. They are a testament to time, to the patient unfolding of cosmic history, to the light that has journeyed across eons to deliver its message. To comprehend this scale is to realize that we do not simply observe the universe. We are woven into it, participants in a story that began long before we existed and will continue long after we're gone. As we move forward in our journey through the cosmos, we carry this number with us. 93 billion light-years, not as a limit, but as a foundation. A reminder that even the vastest measurements are still just the beginning, that beyond every horizon lies another, and that the universe, in its infinite patience, reveals itself one photon at a time. To truly grasp the size of the observable universe, we must begin where all journeys begin, here at home, standing on familiar ground. But we will not stay long. What follows is not merely a catalogue of distances, but a meditation on scale itself, a gradual unveiling of cosmic magnitude that transforms our understanding of distance, time, and our place within the infinite. Let us begin with a single step outward from Earth, into the darkness that has beckoned humanity since we first looked up at the night sky. The first reach. Earth to Moon. The Moon hangs in our sky, close enough to see with naked eyes, yet far enough to humble us. At its nearest, it sits 238,155 miles from Earth. In the language of light, this distance becomes 1.3 light seconds, the time it takes for light to travel from lunar surface to terrestrial ground. When astronauts spoke to mission control from the Moon's surface, their words travelled at the speed of light, yet still arrived with a delay, a cosmic pause in the conversation, a reminder that even our closest celestial neighbour exists in its own pocket of space-time. To reach the Moon takes approximately 3 days of continuous travel. Apollo astronauts made this journey in vessels no larger than a small apartment, crossing a void where no air exists, no sound travels, and Earth gradually shrinks to a blue marble suspended in black velvet. The Moon is humanity's first step into the cosmic ocean, yet it represents only the threshold, the outermost edge of what we might call home. Crossing the solar system, beyond the Moon lies our solar system, a collection of worlds orbiting a single star. The Sun sits at an average distance of 93 million miles from Earth, a measurement we call 1 astronomical unit. Light from the Sun takes 8 minutes and 20 seconds to reach us. When we watch a sunrise, we're observing the Sun as it was over 8 minutes in the past, a phenomenon that becomes increasingly profound as we journey outward. Mars, our nearest planetary neighbour, sits between 34 million and 250 million miles away, depending on orbital positions. Light takes between 3 and 22 minutes to bridge this gap. Radio signals sent to rovers on Mars arrive with this same delay, creating a conversation conducted in slow motion, each question an answer separated by the patient rhythm of cosmic distance. The outer planets stretch this scale beyond immediate comprehension. Jupiter, the giant guardian of our solar system, orbits at a distance of 484 million miles, where light takes 43 minutes to arrive. Saturn, with its ethereal rings, sits nearly 900 million miles distant, where sunlight requires 80 minutes of travel. Neptune, the outermost major planet, circles our Sun at a distance where light takes over 4 hours to complete its journey, a distance so vast that the Sun appears as merely a bright star in its sky. The edge of our solar system, marked by the heliopause where the Sun's influence gives way to interstellar space, lies approximately 11 billion miles away, roughly 17 light-hours distant. Voyager 1, humanity's most distant emissary, has travelled for over 4 decades to reach this boundary, crossing into the space between stars at speeds exceeding 38,000 atom-feet, yet still requiring decades to leave the Sun's domain. The local neighbourhood, nearest stars beyond our solar system, lies a gulf so vast it redefines our concept of distance entirely. The nearest star to our Sun, Proxima Centauri, sits 424 light-years away. This means that light, travelling at 186,282 miles per second, requires over 4 years to cross this void. At current spacecraft speeds, reaching Proxima Centauri would take tens of thousands of years, a journey spanning not lifetimes but entire civilizations. Within a sphere of 100 light-years around Earth, we find thousands of stars, each a sun in its own right, many with planets orbiting in their habitable zones. This is our local neighbourhood, a bubble of stellar systems where, if intelligent life exists, their view of Earth shows humanity as it was a century ago, before spaceflight, before atomic energy, before the modern world emerged. We see them as they were long ago, and they, if they are watching, see us in our own past. This volume of space, 100 light-years in radius, seems vast, yet it represents only a minuscule fraction of our galaxy, a single droplet in a cosmic ocean. The Milky Way, our island universe. Our galaxy, the Milky Way, stretches approximately 100,000 light-years from edge to edge. It is a spiral structure containing between 200 and 400 billion stars, each separated by light-years of empty space, yet all bound together by gravity into a slowly rotating disk. At its center lies a supermassive black hole, millions of times more massive than our Sun, around which the entire galaxy revolves like a cosmic wheel turning through eternity. Our Sun sits roughly 26,000 light-years from the galactic center, positioned in a minor spiral arm. Light from the galaxy's core takes 26,000 years to reach us. When we observe the center of our galaxy through telescopes, we are seeing it as it existed when woolly mammoths walked the Earth, when early humans were just beginning to create art and language. The galaxy we observe is ancient, its light travelling across millennia to arrive in our instruments tonight. To journey across the Milky Way at the speed of light would take 100,000 years. At the speeds achieved by our fastest spacecraft, crossing our galaxy would require hundreds of millions of years, a time span that exceeds the entire history of complex life on Earth. The Milky Way is not just a structure in space, it is a structure in time, a vast assemblage of stars whose light reaches us from different epochs, creating a composite image that exists nowhere else in the universe except in our perception. Our galaxy is not alone in the darkness. The local group, a gathering of galaxies. The Milky Way belongs to a collection of galaxies called the local group, spanning approximately 10 million light-years across. This cosmic neighborhood contains more than 50 galaxies, though most are small dwarf galaxies, faint collections of stars bound gravitationally to the larger members. The two dominant galaxies are our Milky Way and the Andromeda Galaxy, a spiral structure larger than our own, sitting 2.5 million light-years distant. Andromeda is the most distant object visible to the naked eye. When we observe it on a dark night, the photons entering our eyes began their journey 2.5 million years ago, before the genus Homo existed, before humans walked upright, when our ancestors were still distant evolutionary relatives of modern humanity. Andromeda and the Milky Way are drifting toward each other, pulled by mutual gravity, destined to collide and merge in approximately 4.5 billion years, creating a new elliptical galaxy that will dominate the local group. Within the local group, galaxies are separated by millions of light-years, yet they remain gravitationally bound, moving through space together like a fleet of ships sailing across the cosmic ocean. This is the scale where individual galaxies cease to be isolated islands and become part of larger structures, threads in a grander cosmic tapestry. Superclusters and the cosmic web zooming outward still further, we discover that galaxy groups like our local group are themselves part of larger structures called superclusters. Our local group belongs to the Virgo supercluster, which spans approximately 110 million light-years and contains thousands of galaxies arranged in clusters and filaments. At this scale, galaxies appear not as isolated objects but as bright nodes in a vast network, connected by invisible threads of dark matter and separated by enormous voids where almost nothing exists. But even superclusters are merely components of something larger. Recent observations have revealed that our Virgo supercluster is itself part of an even more immense structure called Laniakea, meaning immeasurable heaven in Hawaiian. Laniakea spans 520 million light-years and contains the mass of 100 million billion suns distributed among 100,000 galaxies. At this scale, even the Milky Way becomes invisible, a single point of light lost in an ocean of galaxies, all flowing together through space like water drawn toward a cosmic drain. These structures form what astronomers call the cosmic web, a pattern that emerges when we map millions of galaxies across billions of light-years. Galaxies cluster along filaments, vast threads of matter stretching across hundreds of millions of light-years, separated by enormous voids, empty regions where almost no galaxies exist. The universe at this scale resembles a sponge or foam, with matter concentrated along edges and faces while vast empty spaces fill the interior. This is not random chaos, but structure, pattern emerging from the initial conditions of the Big Bang, shaped by gravity over billions of years. The cosmic web is the universe's architecture, the skeleton upon which all visible matter hangs, massive structures, walls across the cosmos. At the largest scales, we discover structures that challenge our comprehension. The Sloan Great Wall, discovered in 2003, is a vast filament of galaxies spanning approximately 1.37 billion light-years across. It is one of the largest structures ever observed, a wall of galaxies stretching across such immense distances that light takes over 1 billion years to cross from one end to the other. Other structures rival or exceed even this. The Hercules Corona Borealis Great Wall may span up to 10 billion light-years, though its exact size remains debated. These structures exist at scales so vast they approach the limits of what the universe's age allows. There has barely been enough time since the Big Bang for gravity to assemble structures of such magnitude, pushing against the boundaries of cosmological models. At these distances, we are no longer looking at the universe as it is, but as it was. Light from galaxies, 1 billion light-years away, shows us those galaxies as they existed 1 billion years ago, when Earth was dominated by simple multicellular life, when the continents were arranged differently, when the planet itself was younger. The further we look into space, the further we peer into time, until distance and time become inseparable, two facets of the same cosmic dimension. Approaching the edge, the cosmic horizon. As we continue outward, the universe begins to change in fundamental ways. Galaxies appear younger, less organized, their light stretched and reddened by the expansion of space itself. At distances exceeding 10 billion light-years, we observe galaxies as they existed in the early universe, mere billions of years after the Big Bang, when stars were first forming in great numbers and galaxies were just beginning to assemble from primordial gas. The most distant galaxies ever observed lie more than 13 billion light-years away, their light travelling across the expanding universe for over 13 billion years to reach our telescopes. These galaxies appear as they were when the universe itself was young, less than 1 billion years old, when the first generations of stars were transforming primordial hydrogen into heavier elements, when the cosmos was still finding its shape. But distance in an expanding universe becomes complex. Due to cosmic expansion, a galaxy whose light has travelled 13 billion years is not 13 billion light-years away now. It is much farther. As that galaxy's light travelled toward us, space itself stretched, carrying that galaxy away from us even as its light approached. Today, that same galaxy sits approximately 30 billion light-years distant, receding from us faster than light can travel, forever beyond our reach. The edge of the observable universe, the cosmic horizon, lies at a commoving distance of approximately 46.5 billion light-years in all directions. This is the limit of what we can observe, not because space ends there, but because light from beyond this boundary has not had time to reach us since the Big Bang. The universe may extend infinitely beyond this horizon, filled with galaxies, structures, and phenomena we will never observe, existing in a realm forever separated from our cosmic sphere. At this ultimate boundary, we encounter not a wall or edge, but a horizon of time itself. The most distant light we detect is not from galaxies, but from the cosmic microwave background radiation, the afterglow of the Big Bang itself, released 380,000 years after the universe's birth, when space first became transparent. This light has travelled 13.8 billion years to reach us, stretched by expansion into microwave wavelengths, carrying within its subtle variations the blueprint of all structure that would ever form. To journey from Earth to the edge of the observable universe is to travel not just through space but through time, from the present moment backward toward the beginning of everything. It is a journey measured not in miles but in epochs, not in distance, but in the history of creation itself. At the edge, time and space merge into a single concept, and we stand not at a boundary but at the origin, looking back toward the moment when our universe was born from light and energy, when everything we know existed in a space smaller than an atom, waiting to become the cosmos we explore tonight. This is the scale of the observable universe, a sphere 93 billion light-years across, containing everything we can ever detect, observe, or know. And yet it may be only a fraction of what truly exists, a single bubble in an infinite ocean, forever expanding, forever ancient, forever beyond our complete understanding. As we stand at the precipice of cosmic understanding, gazing across 93 billion light-years of observable space, a profound question emerges from the darkness. What is the shape of everything we can see? What architecture underlies the vast expanse we call the observable universe? The answer is both unexpected and humbling. Current evidence suggests that the observable universe is remarkably flat in geometric terms, not flat like a piece of paper, but flat in the deeper mathematical sense that parallel lines remain parallel across cosmic distances, that triangles contain exactly 180 degrees, even when drawn across billions of light-years. This flatness is not intuitive, it is not obvious, yet it is one of the most profound discoveries of modern cosmology. The flatness of space means that if we could somehow measure the angles of an enormous triangle drawn between three distant galaxies, those angles would sum to exactly what Euclidean geometry predicts. No more, no less. This flatness extends as far as we can observe, suggesting that space itself, despite being curved by matter and energy on local scales, maintains an overall geometric simplicity that defies the imagination. It is as though the universe was constructed with a cosmic level, ensuring that its foundation remains true across unimaginable distances. But the universe is not merely flat, it is structured. If we could pull back far enough, beyond the scale of galaxies, beyond clusters and superclusters, we would see something breathtaking. The cosmic web. This is not a metaphor. It is a literal description of the largest structures in the universe. Galaxies do not scatter randomly through space like stars on a painter's canvas. They gather along vast filaments, walls, and nodes that stretch across hundreds of millions of light-years, forming patterns that resemble neural networks or the intricate threads of a spider's web glowing in morning dew. These filaments are rivers of galaxies, flowing along invisible channels carved by gravity over billions of years. Between them lie voids, vast empty regions where almost nothing exists. These voids are not merely spaces between matter. They are the dominant feature of the universe's architecture, occupying more volume than all the galaxies combined. Some voids stretch across 300 million light-years or more, regions so empty that a traveller crossing one would encounter only a handful of galaxies in an ocean of darkness. At the intersections of filaments, where cosmic threads meet, massive galaxy clusters form like cities at the crossroads of ancient trade routes. These nodes contain thousands of galaxies bound together by gravity, their combined mass bending space-time into deep wells that trap light and matter alike. The entire structure, filaments, walls, voids, and nodes, resembles a three-dimensional foam, a cosmic sponge stretched across the observable universe. Yet what we see is only a fraction of what exists. Ordinary matter, the atoms that make up stars, planets, and every living thing constitutes only 5% of the universe's total content. 5%. The rest is hidden, invisible, detectable only through its gravitational influence. This is the realm of dark matter and dark energy, the twin mysteries that dominate cosmic existence. Dark matter makes up 27% of the universe's content. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can directly measure. Yet it is everywhere, woven through galaxies and filaments like an invisible scaffolding that holds the visible universe together. Without dark matter, galaxies would fly apart. Their stars spin too fast for ordinary matter alone to hold them in gravitational embrace. Dark matter provides the additional mass, the unseen anchor that prevents the cosmic web from unraveling. We know dark matter exists because we can see its effects. Galaxies rotate at speeds that should tear them apart, yet they remain intact. Galaxy clusters bend light from distant objects far more than their visible matter can account for. The cosmic web itself, with its filaments and voids, formed because dark matter clumped first, creating gravitational wells into which ordinary matter later fell, igniting into stars and galaxies. Dark matter is the architect of cosmic structure, shaping the large-scale geometry of space invisibly, silently, across billions of years. But even dark matter is dwarfed by something stranger still. Dark energy comprises 68% of the universe's content, and unlike dark matter, it does not clump or gather. It is spread uniformly throughout all of space, a mysterious force that exerts negative pressure, pushing space itself apart. Dark energy is the reason the universe's expansion is not slowing, but accelerating. Galaxies are not merely drifting away from each other, they are being driven apart by a force embedded in the fabric of space itself. Dark energy is perhaps the deepest mystery in all of physics. We do not know what it is. We do not know where it comes from. Some theories suggest it is the energy of empty space itself, a quantum foam that permeates the vacuum. Others propose it is a dynamic field, changing over time, something we have yet to fully comprehend. What we do know is that dark energy is winning. It is overwhelming gravity on the larger scales, stretching the universe faster and faster, pulling distant galaxies beyond the reach of light itself. Together, dark matter and dark energy compose 95% of everything. The universe we can touch, see, and measure directly is a mere sliver, a thin veneer of luminous matter floating atop a vast ocean of the unknown. To understand the universe is to accept that most of it is invisible, that the grand architecture of space is shaped by forces we cannot see, only infer through their effects on the cosmos around us. Despite the presence of dark matter, dark energy, and the complex structure of the cosmic web, the universe appears statistically homogeneous and isotropic at the larger scales. Homogeneous means that on average, every region of space contains the same density of matter and energy. Isotropic means that the universe looks the same in every direction. No matter where we stand, no matter which way we look, the cosmos presents the same statistical properties, the same distribution of galaxies, the same background radiation, the same fundamental structure. This uniformity is remarkable. It suggests that the universe does not have a center, no preferred location, no special direction. Every point in space is essentially equivalent to every other point. This principle, known as the cosmological principle, underpins our understanding of the universe's evolution and fate. It tells us that the laws of physics are the same everywhere, that the universe is governed by consistent rules across all of space and time. Yet this uniformity exists only on the larger scales. Zoom in, and we see structure, complexity, and variation. Galaxies cluster and collide. Stars are born and die. Planets orbit their suns, but pull back far enough, beyond superclusters and voids, and the universe smooths out into a nearly perfect homogeneity, like a textured fabric that appears uniform when viewed from a distance. This flatness, this structure, this composition of dark matter and dark energy, all point toward a future that is both inevitable and melancholy. The universe's fate is written in its accelerating expansion. As dark energy continues to push space apart, the observable universe will paradoxically shrink over trillions of years. This is not a contradiction. It is a consequence of cosmic expansion combined with the finite speed of light. Distant galaxies are already receding from us faster than the speed of light, not because they are moving through space, but because space itself is expanding between us. As expansion accelerates, more and more galaxies will cross the cosmic horizon, the boundary beyond which light can no longer reach us. These galaxies will not disappear suddenly. They will fade, red shifting into infrared, then radio waves, then nothing, their light stretched beyond detection as they slip beyond the edge of observability. In 1 trillion years, perhaps sooner, the night sky will be a lonelier place. The distant galaxies we see today, the Andromeda Galaxy, the Virgo cluster, the great walls and filaments of the cosmic web, will have receded beyond our reach. Future observers, if any exist, will see only the galaxies within their local gravitational group, a small island of light surrounded by an ever-expanding ocean of darkness. Eventually, even those nearby galaxies will merge or drift apart. Stars will exhaust their fuel. Black holes will evaporate through Hawking radiation over timescales so long they defy comprehension. The universe will become cold, dark, and empty, a vast expanse of space expanding endlessly into silence. The cosmic web will dissolve. The filaments will fade. The voids will grow until they encompass everything. What remains will be a universe of isolated particles, separated by distances so great that causality itself becomes meaningless. This is the fate suggested by our current understanding. A universe of eternal expansion driven by dark energy, cooling and diluting until nothing remains but empty space, expanding forever into the infinite future. It is a lonely fate, but it is also distant, so far beyond the present moment that it belongs more to philosophy than to immediate concern. For now, the universe is rich, vibrant, and full of structure. The cosmic web stretches across space like a tapestry, woven from light and gravity. Dark matter and dark energy shape the architecture of existence in ways we are only beginning to understand. The flatness of space hints at deeper symmetries, at a universe fine-tuned or perhaps simply vast beyond imagining. To contemplate the shape, structure, and fate of the observable universe is to confront both our insignificance and our significance. We are small, inhabiting a tiny corner of a vast cosmos, yet we are also observers, capable of understanding, of measuring, of gazing across billions of light years and comprehending the grand design. We are the universe aware of itself, a fleeting moment of consciousness in an expanse of time and space that stretches from the Big Bang to the infinite future. The universe is flat, yet it curves around mass. It is homogeneous, yet structured in intricate detail. It is composed mostly of things we cannot see, yet we can measure their influence with extraordinary precision. It is expanding, accelerating, carrying distant galaxies beyond our reach, yet it remains knowable, understandable, subject to the laws of physics we continue to uncover. In this grand structure, in this cosmic web of filaments and voids, in the invisible scaffolding of dark matter and the relentless push of dark energy, we find not just the universe as it is, but the universe as it will be. A future written in expansion, in entropy, in the slow dimming of light across an ever-growing expanse. To understand this is not to despair, but to appreciate the extraordinary present moment, when the universe is still young, still bright, still full of wonders waiting to be discovered in the darkness between the stars. To know the size of the observable universe is to grasp something that cannot be seen all at once, something so vast it exists beyond the reach of any single instrument. Yet we have measured it, not by travelling to its edge, but by listening to the whispers of ancient light, by reading the subtle signatures left in the fabric of space itself. The story of how we came to know the true scale of the cosmos is not just a story of numbers. It is a story of tools, of human ingenuity reaching across impossible distances, transforming faint signals into profound understanding. These are not merely telescopes and satellites. They are our eyes in the darkness, our ambassadors to the edge of time. The journey begins with a telescope that changed everything. Launched in 1990, the Hubble Space Telescope floated into orbit above Earth's distorting atmosphere, carrying with it the hopes of an entire generation of astronomers. Free from the turbulence of air and weather, Hubble could see the universe with unprecedented clarity. Its mirror, though initially flawed and later corrected, became humanity's clearest window into the deep cosmos. But it was not just Hubble's sharpness that revolutionized our understanding. It was what it chose to look at. In 1995, astronomers pointed Hubble at what appeared to be an empty patch of sky, a region so dark and unremarkable that it seemed devoid of interest. For 10 consecutive days, Hubble stared at this tiny speck of darkness, no larger than a grain of sand held at arm's length. What emerged from that long exposure was nothing short of miraculous. Where darkness had been, thousands of galaxies suddenly appeared, galaxies of every shape and size, some spiral, some elliptical, some distorted by collisions that occurred billions of years ago, each one a universe unto itself, each containing hundreds of billions of stars. This image, the Hubble Deep Field, revealed that even the emptiest regions of space are crowded with galaxies stretching back toward the beginning of time. Years later, Hubble looked even deeper. The Hubble Ultra Deep Field captured galaxies so distant that their light had travelled for over 13 billion years to reach us. We were seeing them not as they are now, but as they were when the universe was still young, still forming its first structures. These observations pushed the boundaries of the observable universe outward, revealing that the cosmos extended far beyond what we had imagined. Hubble did not just measure distance, it measured time. Every galaxy in those images was a fossil, a relic preserved in light, showing us what the universe looked like in ages long past. But to truly understand the observable universe, we needed to look not just at galaxies, but at the universe itself in its infancy. This required a different kind of observation, one that could detect not visible light, but the faint afterglow of creation. In 1989, NASA launched the Cosmic Background Explorer, known as COBE, a satellite designed to map the cosmic microwave background, the oldest light in the universe. This radiation, emitted just 380,000 years after the Big Bang, fills all of space like a quiet hum. It is the echo of the moment when the universe cooled enough for atoms to form, allowing light to travel freely for the first time. COBE's observations were groundbreaking. It detected tiny fluctuations in the temperature of this ancient radiation, variations of only a few millionths of a degree. These fluctuations were the seeds of all structure in the universe. Regions that were slightly denser would go on to form galaxies, stars, and planets. Regions that were slightly less dense would become the vast voids between them. For the first time, we could see the blueprint of the cosmos, written in light so old it predates the formation of the first stars. COBE's measurements gave us a snapshot of the universe when it was smooth, uniform, and unimaginably young. But COBE was only the beginning. In 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, was launched to study the cosmic microwave background with far greater precision. WMAP spent 9 years mapping the infant universe in exquisite detail, measuring not just the temperature variations, but their patterns, their distribution, their geometry. From these measurements, cosmologists could calculate the age of the universe, its composition, and its curvature. MAP told us that the universe is 13.77 billion years old, that it is flat, and that it is dominated by mysterious dark energy and dark matter. These were not guesses, they were measurements, precise to within a fraction of a percent. Then came Planck. Launched by the European Space Agency in 2009, the Planck satellite refined WMAP's observations even further, producing the most detailed map of the cosmic microwave background ever created. Planck's data allowed scientists to measure the universe's expansion rate, its total energy content, and the exact proportions of ordinary matter, dark matter, and dark energy. It revealed subtle acoustic oscillations in the early universe, frozen into the pattern of the cosmic microwave background like ripples on a pond. These patterns confirmed that the observable universe is not just large, it is precisely measurably large, extending 46.5 billion light-years in all directions, even though the universe is only 13.8 billion years old. Yet mapping the infinite universe was only part of the story. To measure distances across billions of light-years, astronomers needed cosmic mile markers, objects whose brightness was known and consistent. They found them in type Ia supernovae, exploding stars that occur when a white dwarf reaches a critical mass and detonates in a thermonuclear explosion. Because these explosions always release the same amount of energy, they shine with predictable brightness. By measuring how dim they appear from Earth, astronomers could calculate their distance with extraordinary accuracy. In the late 1990s, 2 independent teams used Type Ia supernovae to measure the expansion of the universe across cosmic time. What they discovered was shocking. The universe's expansion was not slowing down as many had assumed. It was accelerating. Distant supernovae appeared dimmer than expected, meaning they were farther away than they should be if the universe were expanding at a constant rate. This discovery revealed the existence of dark energy, a mysterious force driving the universe to expand faster and faster. These supernovae became standard candles, beacons lighting the way across billions of light-years, allowing us to trace the history and scale of the observable universe with unprecedented precision. Now, a new generation of instruments is pushing even further. Launched on Christmas Day in 2021, the James Webb Space Telescope represents the most powerful observatory ever placed in space. Unlike Hubble, which observes primarily in visible light, Webb observes in infrared, allowing it to see through cosmic dust and detect the faint heat signatures of the universe's first galaxies. Within months of beginning operations, Webb detected galaxies formed just 300 million years after the Big Bang, some of the earliest structures ever observed. These galaxies appear as faint red smudges, their light stretched by the expansion of the universe into wavelengths only infrared instruments can detect. Webb's observations are rewriting our understanding of cosmic history. The galaxies it has discovered are larger, brighter, and more mature than expected, suggesting that the universe assembled its first structures faster than we believed possible. Every image Webb captures pushes the frontier of the observable universe closer to the Big Bang itself, revealing a cosmos that is not just vast, but astonishingly active in its infancy. Webb does not just see farther, it sees deeper into time, unveiling epochs of the universe that were previously hidden from view. On the ground, vast surveys are mapping billions of galaxies to reveal the large-scale structure of the universe. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, has catalogued the positions and distances of over 1 million galaxies, creating a 3-dimensional map of the cosmic web. This web is not random, it is structured, with galaxies clustered along vast filaments of dark matter, separated by enormous voids where almost nothing exists. These surveys show us that the observable universe is not a uniform expanse, but a network of interconnected structures shaped by gravity over billions of years. But light is not the only messenger from the cosmos. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, ripples in space-time caused by the collision of 2 black holes over 1 billion light-years away. These waves travel at the speed of light, carrying information about some of the most violent events in the universe. Unlike light, gravitational waves are not absorbed or scattered by matter. They pass through everything, arriving at Earth with their information intact. LIGO and its successor, Virgo, have since detected dozens of gravitational wave events, from colliding black holes to merging neutron stars, opening a new window on the universe's most extreme phenomena. Radio telescopes, too, are probing the universe's earliest epochs. Arrays like the Atacama Large Millimeter, Submillimeter Array, ALMA, study the cold gas and dust that fill the space between stars and galaxies. These observations reveal how the first stars formed, how galaxies evolved, and how the universe transitioned from a smooth, featureless expanse into the richly structured cosmos we see today. Radio telescopes can detect signals from neutral hydrogen, the most abundant element in the universe, allowing astronomers to map regions that are invisible to optical telescopes. Looking ahead, the next generation of instruments promises even greater revelations. The extremely large telescope, currently under construction in Chile, will have a mirror over 39 meters across, larger than any optical telescope ever built. It will be capable of directly imaging exoplanets, studying the atmospheres of distant worlds, and observing the universe's first galaxies with unprecedented detail. The square kilometre array, a network of thousands of radio antennas spread across continents, will map the distribution of hydrogen throughout cosmic history, tracing the evolution of the universe from the Dark Ages following the Big Bang to the present day. Space missions planned for the 2030s will carry instruments sensitive enough to detect the faintest signals from the edge of the observable universe. These missions will study gravitational waves with greater precision, map the cosmic microwave background with even finer resolution, and search for signs of the universe's earliest moments. Each new tool extends our reach, sharpens our vision, and deepens our understanding of the cosmos. These instruments are not just machines. They are extensions of human curiosity, built to answer questions that have haunted us since we first looked up at the night sky. How big is the universe? How old is it? What is it made of? Where did it come from? Every telescope, every satellite, every detector is a bridge between the human mind and the infinite. They transform the invisible into the knowable, the distant into the measurable. To measure the observable universe is to measure time itself. It is to capture the light of stars that died before Earth was born, to map the distribution of matter across billions of years, to listen to the echoes of creation still reverberating through space. These tools have revealed that the observable universe extends 93 billion light-years across, a distance so vast it encompasses hundreds of billions of galaxies, each containing hundreds of billions of stars. Yet this measurement is not final. It is a milestone, a marker on a journey that continues. As we develop more powerful instruments, we will see farther, deeper, and with greater clarity. We will measure the universe with increasing precision, refining our understanding of its size, its age, and its fate. But no matter how far we look, there will always be a horizon, an edge beyond which light has not yet had time to reach us. The observable universe is not everything that exists. It is only everything we can see. In the silence of space, these instruments keep watch, collecting photons that have travelled for billions of years, measuring gravitational waves that ripple through the fabric of reality, mapping the structure of a cosmos too vast for any single mind to comprehend. They are our witnesses to the infinite, our tools for touching the untouchable, and as long as we continue to build them, to launch them, to listen to what they tell us, we will continue to push back the darkness, one measurement at a time, uncovering the true scale of the universe we call home. At the edge of the observable universe, we encounter not just a boundary of space, but a wall of comprehension itself. The numbers we have explored, the vast distances measured and calculated with exquisite precision, all lead us to a profound and unsettling realization. We can see only so far. Beyond that horizon, beyond the reach of light that has had time to travel to us since the beginning, lies something we may never know. Not because our instruments are insufficient, not because our mathematics are incomplete, but because the universe itself draws a curtain across infinity. What exists beyond our observable horizon is not hidden by darkness. It is hidden by time. The observable universe, with its 93 billion light-year diameter, represents everything we can theoretically see, measure, or detect. But this does not mean it is all that exists. In fact, Most cosmologists believe the universe extends far beyond what we can observe, perhaps infinitely. The light from those distant regions has not yet reached us, and depending on the expansion of space, it may never reach us. We stand at the centre of our own cosmic bubble, able to peer outward in all directions, yet forever confined within a sphere defined not by walls, but by the speed of light and the age of the universe. To contemplate what lies beyond is to engage with the unknowable, to accept that some questions may have no answers, not now, not ever. This realization forces us to confront a fundamental assumption known as the cosmological principle. This principle suggests that the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations. Our observable patch of the cosmos, according to this idea, is representative of the whole. The galaxies, the cosmic web, the distribution of matter and energy we see here would be mirrored everywhere, even in regions we can never observe. It is a comforting thought, one that allows us to extrapolate from what we know to what we cannot see. But it is also an assumption, not a proven fact. What if the universe beyond our horizon is radically different? What if the laws of physics themselves vary across unimaginably vast distances? We have no way to know. The cosmological principle is an act of faith, grounded in observation but extended beyond the reach of verification. This brings us to one of the most staggering ideas in modern cosmology, the concept of the multiverse. If our observable universe is just one bubble in a vastly larger reality, then these numbers we have been discussing may be almost meaningless in the grander scheme. According to certain interpretations of quantum mechanics and inflationary cosmology, the Big Bang that created our universe may not have been a singular event. Instead, inflation, the rapid expansion that occurred in the first fractions of a second, may have spawned countless other universes, each with its own properties, its own laws of physics, its own observable horizons. These universes, if they exist, would be causally disconnected from ours. No light, no information, no signal could ever pass between them. They would exist in parallel, forever separate, each one its own cosmos, its own infinity. Our 93 billion light-year observable universe would be one bubble among an infinite froth of universes, each as real and vast as our own, yet forever beyond our reach. Within the framework of the multiverse, an even more unsettling question emerges. Why is our universe the way it is? The physical constants that govern reality, the strength of gravity, the charge of the electron, the rate of cosmic expansion, all appear to be finely tuned to allow for the existence of matter, stars, planets, and ultimately life. Change any one of these constants by even a tiny fraction, and the universe would be radically different. Stars might never form, atoms might never hold together, and life as we know it would be impossible. This fine-tuning has puzzled scientists and philosophers for decades. Is it mere coincidence? Is it evidence of design? Or is it a consequence of the multiverse? If countless universes exist, each with different physical constants, then it's inevitable that at least one would have the right conditions for life. We exist in this universe not because it is special, but because we could not exist in any of the others. We are not the product of intention, but of probability across infinite iterations. The fine-tuning of our universe may not be miraculous. It may simply be selection bias on the grandest scale imaginable. But even the multiverse does not answer every question. Some cosmologists propose that the universe, while larger than the observable region, may still be finite. Instead of extending infinitely in all directions, the universe could be wrapped in higher dimensions, shaped like a hypersphere or a torus, folding back upon itself in ways we cannot directly perceive. In such a universe, if you travelled far enough in one direction, you might eventually return to your starting point, not because you looped around in ordinary space, but because space itself is curved in dimensions beyond the three we experience. Such a universe would be vast beyond comprehension, yet ultimately bounded, a cosmic hall of mirrors reflecting the same structures endlessly across its curvature. If this is true, then the observable universe is not a sample of infinity, but a glimpse of a finite, though unimaginably large, whole. The philosophical implications of these ideas weigh heavily upon the mind. We live on a planet orbiting an ordinary star, one of hundreds of billions in a galaxy that is itself one of hundreds of billions in the observable universe. And if the multiverse exists, our entire observable cosmos may be but one infinitesimal speck in an ocean of universes. Humanity's place in this hierarchy of scales is almost incomprehensibly small. Every triumph, every struggle, every moment of joy and sorrow in human history has occurred on a pale blue dot, drifting through a vast and mostly empty cosmos that may itself be a negligible fragment of something far greater. This perspective can be humbling to the point of despair. Yet it can also be profoundly liberating. If the universe is so vast, so indifferent, then the meaning we create, the connections we forge, the beauty we recognize, all become acts of defiance against the void. We are not diminished by the scale of the cosmos. We are made remarkable by our ability to comprehend it. Yet even after measuring the size of the observable universe, calculating its age, mapping its structure, and theorizing about what lies beyond, one question remains unanswered. Why is there something rather than nothing? The universe, in all its vastness, exists. But why? Why does space exist at all? Why does time flow? Why do the laws of physics operate with such consistency? These are not questions that astronomy or cosmology can answer with telescopes and equations. They are questions that touch the edge of philosophy, theology, and existential mystery. The size of the observable universe, its 93 billion light-year span, tells us how far light has travelled and how space has expanded. But it does not tell us why there was a beginning in the first place, why there was a big bang rather than eternal nothingness. Some propose that the universe emerged from quantum fluctuations, that nothingness is inherently unstable and destined to produce something. Others suggest that the universe is eternal, cycling through endless iterations of birth, expansion, and collapse. Still others invoke the multiverse again, proposing that universes spontaneously generate from the quantum foam of higher dimensional space. But none of these answers feel complete. They push the question back one level without resolving it. If quantum fluctuations create universes, why do quantum mechanics exist? If the multiverse spawns infinite cosmos, what sustains the multiverse itself? At the deepest level, existence remains a mystery wrapped in an enigma hidden behind a veil we may never fully pierce. What we do know is our cosmic address, the series of nested scales that locate us within the observable universe. We live on Earth, the third planet from the Sun, a medium-sized star in the Orion arm of the Milky Way galaxy. The Milky Way is part of the Local Group, a collection of about 50 galaxies bound together by gravity. The Local Group is a small suburb within the Virgo supercluster, which in turn is part of the even larger Laniakea supercluster, a structure spanning 520 million light-years. And Laniakea itself is just one feature within the cosmic web, the vast filamentary structure of galaxy clusters and voids that stretches across the entire observable universe. This is our address, written in the language of cosmology. And yet, if the universe extends beyond the observable horizon, if the multiverse exists, if reality is vaster than we can ever comprehend, then our address is incomplete. We know where we are within what we can see, but we do not know where we are within the whole. Standing at the edge of everything, armed with the knowledge of the observable universe's true size, we are left not with certainty, but with wonder. The 93 billion light-year diameter we have calculated is not an ending, but a beginning. It is the boundary of what we can know, the limit of our cosmic horizon, but also an invitation to imagine what lies beyond. Every answer we have uncovered has given birth to new questions. Every measurement has revealed deeper mysteries. The universe is not a puzzle to be solved, but an endless frontier to be explored, one horizon at a time. Perhaps the most profound implication of all is this: the universe does not owe us answers. It does not arrange itself for our comprehension. It simply is, vast and silent, indifferent to our curiosity, yet endlessly generous in revealing its wonders to those patient enough to look. The fact that we, tiny beings on a small world, can measure the observable universe, can trace the journey of light across billions of years, can contemplate multiverses and higher dimensions and the nature of existence itself. This is perhaps the greatest wonder of all. We are the universe becoming aware of itself, consciousness arising from matter, meaning emerging from chaos. In our smallness, we contain something infinite, the capacity to wonder, to question, to reach beyond ourselves toward the unknowable. The observable universe is 93 billion light-years across. But the true measure of the cosmos is not in light-years or parsecs. It is in the questions we dare to ask, in the boundaries we push, in the mysteries we embrace rather than fear. We may never know what lies beyond our cosmic horizon. We may never understand why there is something rather than nothing. But we can stand at the edge of the known universe, look out into the darkness, and feel not despair, but awe. For in that darkness lies not emptiness, but possibility. And in that possibility lies the eternal promise that there is always more to discover, always farther to journey, always deeper to see. The universe may be indifferent, but we are not, and that makes all the difference. We have travelled far, not just in imagination, but in understanding. From the familiar curve of Earth to the shimmering rings of Saturn, from the nearest stars to galaxies clustered at the very edge of perception. And now we stand at the threshold of comprehension itself, gazing outward at a cosmos so vast that numbers cease to carry meaning. The observable universe stretches 93 billion light-years across, a measurement so profound it exists beyond human intuition. Within this sphere drift more galaxies than grains of sand on all the beaches of Earth. Each galaxy harbours billions of stars. Each star may cradle worlds we will never see. And yet, even this incomprehensible expanse represents only what light has had time to reach us since the beginning of everything. This measurement is not merely a number. It is one of humanity's greatest intellectual achievements. For millennia, we gazed upward and wondered. We told stories of gods and giants, of celestial spheres and infinite waters, but through observation, mathematics, and the patient work of countless minds across generations, we have done something extraordinary. We have measured the edge of visibility itself. We have peered through time and space to map the boundaries of what can be known through light alone. In understanding the scale of the observable universe, we have stretched the limits of human thought to encompass distances that dwarf our world, our sun, even our galaxy, reducing them to infinitesimal points in an ocean of darkness. But this is not the end of the story. It may only be the beginning. The observable universe is bounded not by walls, but by time and the speed of light. Beyond what we can see, the universe may continue indefinitely, perhaps infinitely. Some theories suggest that our observable sphere is but one bubble in a vast cosmic foam, each region expanding, evolving, governed by laws we may never witness. The true extent of reality may dwarf even the 93 billion light-years we have measured, stretching outward into dimensions we cannot yet imagine. What we call the edge is not a boundary, it is a horizon, forever receding as time marches forward and light continues its ancient journey toward us. The universe does not reveal its secrets easily. Each generation has peered deeper, measured more precisely, uncovered layers of complexity hidden within the darkness. From Galileo's telescope to the Hubble Space Telescope, from Edwin Hubble's observations of galactic redshift to the cosmic microwave background mapped by satellites, each tool has expanded our view. And still, the cosmos surprises us. Dark matter, dark energy, the accelerating expansion, each discovery raises new questions, suggesting that what we understand is only a fraction of what exists. The universe is not finished showing us its wonders. As our instruments grow more sensitive, as our theories become more refined, we will continue to push against the edge of everything, measuring, questioning, and marveling at the grand design. In this vast expanse, we are impossibly small, a single planet orbiting an ordinary star in an unremarkable galaxy, adrift in a cosmos too large to fully comprehend. And yet, somehow, against all odds, we have learned to measure it. We have looked outward and inward, combining observation with mathematics, patience with curiosity, and discovered not just how big the universe is, but that we possess the capacity to know it at all. This, perhaps, is the most remarkable fact of all. In a universe of such staggering scale, consciousness has emerged that can contemplate its own place within it. We are the universe observing itself, a way for the cosmos to know its own dimensions. If this journey through the observable universe has stirred something within you, we invite you to share it. Leave a comment below and let us know where you are listening from, whether you're drifting off to sleep beneath the stars or pondering the cosmos in quiet reflection. Subscribe to join us on more journeys through space, time, and the mysteries that fill the darkness. Each video is crafted to help you explore, to wonder, and perhaps to rest beneath the infinite. And if you found value in this voyage, a like helps us reach others who seek the same cosmic comfort. As we close, consider this. The universe is 93 billion light-years wide, filled with more galaxies than we can count, more worlds than we will ever visit. And yet, in understanding how vast it truly is, we also discover something profound about ourselves. We are small, yes, but we are not insignificant. We are the ones who measure, the ones who question, the ones who stand at the edge of everything and dare to look beyond. In the end, the universe is not just something we observe, it is something we are part of, woven into its fabric, connected by gravity, by light, and by the simple, stunning fact that we exist at all.